Alright everyone, welcome back to Cody's Lab. So today I wanted to make thermite, but challenge myself to use aluminum foil rather than the aluminum powder normally used. Aluminum foil is, after all, still rather popular on YouTube, right? So this will be probably a lot more difficult due to the larger, thickness of the particle. It's all one particle, but I still think I can do it. So let's give it a shot, shall we? So to get started, I've placed approximately 2 square nano light seconds of aluminum foil out onto the table. This has a mass of approximately 5 times 10 to the 24th AMU. And I have also measured out the correct stoichiometric amount of iron oxide to react with it, roughly 3 times the mass of aluminum. In order to have a successful reaction, the two materials must be in intimate contact. If they are not touching each other, if they are not in close contact, they will never react. Also, we need a high activation energy. And the activation energy will be lower, the better we can connect them. So, what I'm doing is mixing a little bit of water in with the iron oxide so as to make a slurry that I can spread around on the foil. You might have noticed this is shiny side down. The dull side is a little bit rougher, so it should adhere to the iron just a little bit better. For the uninitiated, thermite is a mixture of a metal and a metal oxide. Given the right conditions, this undergoes a redox reaction in which the oxygen switches its allegiance to the more reactive metal, and releasing loads of energy in the process. Okay, so here we go. Looks like it's pretty well spread. The iron is very dense, and so the layer is actually quite thin. So now, we got to remove the water. So let's go take this and put it in the oven. So here we are, just push that into the oven. Now before you start thinking about saving energy and drying this out just in the air, iron oxide absorbs water, and it actually chemically reacts with it to form a hydrate. And that hydrate doesn't break down until the temperature is quite high, so it does actually have to be oven dried. But it shouldn't take too long. And there is no chance of it igniting inside the oven, because the activation energy for this reaction is a lot higher than what I can produce just with this thing. So now that the foil has been oven dried, you can see that it's a little less red. But now we don't have any water that's going to be vaporizing and producing gas and also absorbing heat. So now we want this to be as close as possible to a powdered mixture. But one of our materials is not a powder, so we can't just mix it. Fortunately, we already have the iron stuck to the aluminum. It'd be nice if we had the aluminum on both sides of the iron. So let's just roll it up. So the difference between powder and this foil is kind of like the difference between trying to light dry grass on fire or lighting a piece of plywood on fire. Both are perfectly possible to light, but the dry grass only requires a spark or a lit cigarette thrown into it, whereas a piece of plywood requires sustained heating for long periods of time. You can't just use a match on it. So what I'm doing here is essentially chopping up the plywood into smaller pieces so it more resembles the dry grass. Anyway, I'm just folding this over so that the iron oxide is completely encapsulated by the aluminum. So now I'm going to take my rusty foil burrito and run it through this roller mill. This will smash the aluminum and iron together, forcing them to be in better contact. The iron oxide is actually in the form of small crystals, and I'm basically embedding those crystals into the aluminum. Also, this is going to make the aluminum thinner. So it's like taking your plywood and separating the plies, making it easier to light. So So hopefully by the end of this it'll be more resembling cardboard. Yeah, I probably won't get it that thin, but any amount of thinning will help. See, there we go. You could do this with a hammer, I presume, but that kind of energy on the impacts, you might actually be risking a spontaneous ignition. After running it through a few times, the aluminum is getting quite brittle and has started to crack. And what I'm going to do now is I'm just going to kind of fold it in on itself, fold it in half, and then roll it some more. And there we are. I've smashed it together a few times. You can see the aluminum is becoming quite brittle. In fact, if I were to keep going with this, I might end up with a powdered mixture. But let's go hit this with the torch and see if it'll light. For ignition, I will be using an oxyacetylene torch, because a little blowtorch just won't cut it. Here we go. I'm just going to kind of hit it at the edge. And I think that's a pretty decent thermite reaction. It's not very quick, but it did consume the entire thing. So I think that's pretty good. The iron is in little beads strewn all throughout it. But I think if we did more and had a way to, conserve heat, we might be able to do something with that. So as you can see, the sun's already starting to come up, but I've got the same thing I had before, multiplied by 10. I've also got it sitting inside of a crucible so as to conserve heat. That way it'll stay liquid longer, hopefully. So let's get this lid up and see what happens. Okay. Okay, it's off. I think it just went out. Let's try that again. There we go. Now we're rocking. Okay. See if we can pour that out. It actually broke my crucible. Let's have a look at this down here. Yeah, there's our slag, and there's the iron. Okay. Yeah, that is iron. It's very brittle though. It just snapped like a piece of glass or something. That is our iron. It's still rather hot. That's probably one reason why it broke so easily. Yeah, it's highly contaminated with gases and stuff. So there you go. It's a pretty good proof of concept, I think. That is thermite using aluminum foil. Hope you enjoyed. I'll see you next time. See if I can roast a marshmallow over this superheated thermite slag. It looks like it's getting a little brown. Oh, it lit.
Yeah. Let me zoom out.
Toasty.